All right, so I got this problem from my friend. I don't really know if I should say his name, but if you know, you know. I'm not gonna read this whole thing, but basically, you have a really flexible, uniform chain, and it has like mass M, length L, and you're just holding it so that the end of the chain is just barely touching the floor, right? And you let go. And what you'd imagine to happen is all as it falls, the lengths kind of group up in this little pile, and it falls, and the pile gets bigger. So the question asks, what is a force? Voice crack. What is a force by the table on the chain at any instant in terms of the weight of the chain that's already on the table at that moment? So when I first saw this problem, like in a really silly way, I said, "Hey, friend, wouldn't the force just be equal to the weight of the chain already on the table? Because it's not accelerating." And he correctly pointed out that there is some sort of impulsive force, right? You have the force that is keeping the chain from accelerating downwards, the chain pile, but there needs to be an additional upward force that stops all of the links from coming to rest, right? Because essentially what's happening is each link, as soon as it hits the table, it comes to rest somewhere here. Like we're making that assumption that they essentially instantaneously come to rest. So there's going to be a greater upward force than just the weight of the pile. The question becomes how much greater. So let's think about this. If I were to model this with a little drawing, I have my pile that's already on the thing. I'm just drawing it like a dome. And I have, using a line, I have the chain that's still falling down. And I can draw like a little thing here to signify that this is L, right? This is the original length. We'll say this is H, and we'll assume it's a really small pile. We don't need to make it this big, but we'll say this is H, like the height that's still above, it's still falling, and we'll call this difference L minus H, right? That's the height difference, right? That has fallen so far. So if I want to think about this problem, it helps to draw an FBD. I have still a stuffy nose, so that's why I sound like this. But if we think about the forces, right? As soon as, and remember, we're dealing with links, right? So we have, if you think about our FBD, we have the weight of the pile, which I'll call W. And this is also equal to, well, let's just think about it. There's going to be, my dad's calling me. Hopefully it's not important. I think they're just sleeping. Wait, just give me a second. Yeah? I think they went on. I think they're just letting me know they're leaving. Because I'm not a college student, by the way. I'm not even a teacher. I'm still in high school, so I still live with my parents. Because some people think I'm like a full-grown teacher. I'm not. That'd be really cool. We have the weight of what the pile. So let's think about this, right? Let's let lambda be the total mass over the total length, and we're gonna assume the mass is uniformly distributed, right? Each link has the same mass as every other link. It's not like one side of the chain is heavier because those links have more mass. So in this case, the total mass over the total length is going to equal the mass that is on the thingamabob, the pile, the mass in the pile over, well, it's going to be the length of the pile, but not like this length. I mean like the length of the pile if you were to unravel it, right? What length is on the pile? Well, I know H amount of chain, wire. Did I say wire? I'm sorry. H amount of chain is here, so the pile is made up of L minus H length, if that kind of makes sense. L minus H length. So if this is lambda times L minus H would give me the mass. So this is really going to equal lambda L minus H times G. All right. So now there's going to be the force. Okay, I guess I should draw it as one force because the table is doing this. But there's going. Let's do it like this. There's gonna be the first force by the table. Force table 1, which I guess I'll say force normal. Force normal 1, which balances out the weight, right? It's going to equal the weight. But then there's going to be the force on the chain. So force on the link, an individual link. Because here's the deal, right? These are links. So if I take something rigid, like a ruler, when I drop it, like the force, I believe, I'm not too much of an expert. I'm not a mechanical engineer, really, and I know this is kind of the stuff they study. But the force exerted on the ruler, because this is really a rigid object and it's not really flexible, the force kind of propagates, I believe. So that's why, like, hey, not like the whole ruler moves, not just the area where I inserted the force. But the deal with the link is if you imagine this, if I have two links like this, when one of them stops, the other one keeps going. So the table's only applying a force essentially to one link, I believe. I'm not too much of an expert, but by using that kind of logic, you actually get the correct solution. So there's going to be the force on the link. So let's think about this, right? The force on the link, is really the net force of the link. So F net of the link is going to equal the force of the link. Now, in reality, there is gravity, but it's like the weight of the link is negligible. So we're going to say no, none of that. But what we do know is that the force on the link is going to equal the change in momentum over time, right? This is the impulse. I think this is some sort of, is this the impulse, like the momentum impulse theorem? I don't know. This is just a relationship though. We know the change in momentum over a change in time is going to equal the force on the link. Well, what is the change in momentum? Well, dp is going to equal the very small change in momentum is going to equal m, or dm in this case, right? This link ideally has such negligible mass, we essentially think of this as dm. All right, dm times the change in v. Well, what's the change in v? Well, the change in v is going to equal v final minus v initial. V final is going to equal 0, and v initial, and this dp is going to, I guess, be negative because it's the change in momentum. Oh no, it's positive because v initial would be negative. So it's a change in momentum upward. But that doesn't matter. V initial, well, what is the speed of the link before it lands? Well, if we think about conservation of energy, right, UG, the initial UG of the link, because it's dropped from rest, is going to equal the kinetic energy by the time it hits the table. Well, if I think about any link on this thing, this bottom link has fallen a distance L minus H, right? Because if I were to shift this whole thing back up, each link by this time has fallen the same distance L minus H. So I'm going to say, well, the UG is going to equal the change in UG, really, dm times g times the height L minus H is going to equal 1/2 dm v squared. So I get, a very classic result. V squared is going to equal 2g L minus H. Let's just keep it like this because you're going to see in a second. Well, dm, what I'm going to do, and this is not entirely clear like why you would do this initially, but what I'm going to do is I'm going to say, well, hey, what is a dm? Well, my dm is just going to equal lambda, because this is uniformly a uniformly distributed thing. It's going to equal lambda times the small length, very small length dl that the link makes up, right? So, and this just comes from, right, lambda, right, would also equal dm over dl, and then I just move over the dl. So this is really dm. My change, and I still have this change, I have this v. I'm just going to write v for v. And then what you're going to see is, well, hey, let's take the time derivative, right? So I'm going to do d of dt, and I know this is kind of bad notation, but we'll roll with it. D of dt on both sides, right? If I were to take the time derivative, I get dp dt, right, which is the force on the link, which is approximately the force on the link, very, very close to it because it's so, the weight is so negligible. But F net is going to equal lambda, which is a constant, dl dt, and then v, here's the thing, v is kind of a constant because v just represents the initial velocity, so the initial velocity before it hits a table, that has to be a constant. Well, what is dl dt? The change in length per time of the chain, well, that just ends up being the velocity. So I get lambda v squared. And v squared is 2g, that stuff. So I get 2 lambda g L minus h. So the total force on by the table is going to be, so F is going to equal Fn1, right, the balancing weight, plus F link, the force on the link. Well, hey, Fn1 is going to be, it's going to equal weight, right? Just the part of the force that balances out the weight of the pile. And then the F link is going to be this stuff, 2g lambda, or let's do it like this. Just for giggles, let's do this like, let's rearrange this to 2 lambda, and you might see where this is going, L minus hg. Well, hey, this is just equal to the weight of the pile. This is W. So in the end, I get W plus 2W, which ends up being 3W. That is a pretty crazy result. It's not just W, which we thought initially, it's 3 times it, which I think is a little unintuitive, but it's pretty interesting. It's a pretty fascinating result. So yeah, thank you for watching, and thank you to the person who gave me this problem. He always gives me genuinely fascinating problem. Like this was a whole buttload of fun.